Okay, welcome to this video. This video is going to be an example of computing the equivalent resistance of a fairly complicated resistor network. And so we have the resistor network here. The way we will do this is we'll find series and parallel combinations, replace them by the equivalent series or parallel value, and just keep combining things until we've gotten to the point where we have just one resistor. So again, I like to try to give real-world examples. This particular network isn't very real-world, but it's hard. It will bring out, hopefully, some misconceptions that we can clear up. So let's start. The first thing we need to do is figure out where we can combine something. So if we look at this 10k ohm resistor and this 10k ohm resistor, you'll notice that these are in series because any current that goes through one resistor has to go through the other resistor. And if I have two resistors that are in series, their equivalent resistance will be the sum of the two. So in this case, the equivalent resistance is going to be 20k ohms. Okay, if I look at the bottom part of this circuit, I have essentially the same sort of thing. I have these two resistors, and again, these two are in series because any current that goes through this 10k ohm resistor has to go through this 10k ohm resistor. So the equivalent resistance of these two will be 20k ohms. Okay, now at this point I can't find any other series or parallel combinations that I can use to simplify the network. So it looks like it's time to redraw my network. And I'll do that, hopefully not having everything too smashed together. Okay, so we have our first 20k ohm equivalent resistor and our second equivalent 20k ohm resistor, and all the other resistors are still 10k. Okay, so now we want to see if we can find some series or parallel combinations. And at this point, I'm guessing about a third of you that are watching this video will look at these two guys and say, oh, they look to me like they're in series because we have this guy on top of this guy. But it turns out that they are not in series, because if you look at the current that goes through the top 20k resistor, it can conceivably go through this wire to somewhere else. It's not all going to have to go through this 20k ohm resistor. So these two are not in series, even though visually they look like they might be. The same argument holds for these two 10k ohm resistors. They're not in series because, again, there's some place for the current to go between the two resistors that doesn't include either of the resistors. It can go this way. Well, what else might we try? If we look at things somewhat carefully, we can see that this is a node, this is a node, and this is a node. And the fact that each of those are a node means that we actually have two parallel combinations. So this 10k ohm resistor and this 20k ohm resistor actually form a parallel combination because each of the resistors is connected to the two same nodes. So we have a 10k ohm in parallel with a 20k ohm resistor, which means that the equivalent resistance will be given by 10k ohms times 20 k ohms over 10 k ohms plus 20 k ohms. And if you work this out, you should get an equivalent resistance of 6.67 k ohms. And I'll let you work that out. You have to remember, since these are k ohms, to actually do this as 10 times 10 to the third, 20 times 10 to the third, and so on. Okay, but in any case, I have here that this equivalent resistance is 6.67 k ohms. If you look carefully, you'll see that there is another combination. Where's a beautiful color here? We'll do this in gray. We have this combination here, which is also in parallel, in the sense that the 10 k ohm resistor and the 20 k ohm resistor are both connected between the same two nodes. And so, since it's 10 k ohms in parallel with 20 k ohms, my computation that I did for the first parallel combination still applies. So this one also has an equivalent resistance of 6.67 k ohms. So at this point, let's redraw the network and see what we've got. So I have 10 k ohms. Let's see, this one was in light blue. I have now 6.67 k ohms. I have another 6.67 k ohms. And finally, 10 k ohms from my original resistor there. So now I look at this and I say, are there any series or parallel combinations that I can use? And it turns out that, fortunately enough, this whole set of resistors is one series combination. Again, any current that goes through here ends up going through the blue resistor, the gray resistor, and the other yellow resistor. So these guys are in series. So what that says is the equivalent resistance will be the sum of the resistances. And that sum is given by this expression, which, if I work it out in my head, I'll probably get it wrong, but we'll try anyway. Should be 33.4 k ohms. Okay, so that implies then that this whole network can be replaced by an equivalent 33.4 k ohm resistor. Okay, so that pretty much wraps up this this video. Hopefully this has given you some understanding of how to use combinations of parallel and series components, or in this case resistors, to compute equivalent resistors. So, thanks for watching.